Every single charged particle in the universe projects a continuous force field into the three-dimensional vacuum surrounding it. We map this spatial influence using equipotential surfaces. These represent continuous boundaries in space, where the electric potential, or voltage, is identical at every coordinate. These four absolute rules govern how these surfaces behave, defining their interaction with work, field lines, and each other. These axioms are derived by modeling specific physical geometries and applying strict thermodynamic constraints. Mastering these rules allows us to perfectly map the potential landscape of any electric field in the universe. Attention centers on the final constraint. The electrostatic work done moving a charge along one of these surfaces is strictly zero. Standard physical equations dictate that electrostatic work equals the charge of a particle multiplied by the change in potential. Because an equipotential surface maintains a constant voltage, the change in potential between any 2 points on that boundary is exactly zero. Consequently, an object moving along this specific path requires no energy input or output to maintain its trajectory. The demand for zero work creates a physical necessity that forces equipotential surfaces into rigid, unyielding shapes. Consider the basic building block of electrostatics, a single isolated positive point charge. This point charge emits an electric field radiating perfectly outward in all directions, like spokes on a wheel. The concentric circles surrounding the charge represent boundaries of constant potential. In three-dimensional space, maintaining a constant radius from a central source mathematically guarantees a perfect sphere. The inner spherical surface holds a specific potential value, V1, while the outer sphere holds a different value, V2. This illustrates a potential gradient, where voltage decreases as we move further from the positive source. Specifically, the potential of the inner sphere, V1, is mathematically greater than the potential of the outer sphere, V2. The radial symmetry of a point charge forces its zero work boundaries to form nested concentric spheres. We now shift scale to a different charge distribution, an infinitely large, flat, positively charged sheet. The electric field generated by this plate is a uniform field, featuring parallel, straight vectors moving to the right. A family of flat planes slices vertically through these field lines. In a uniform field, points equidistant from the source form perfectly flat, parallel planes. The closest plane is the high potential boundary, and the further represents the low boundary. Potential drops in the field's direction, confirming V1 is greater than V2. These parallel planes perfectly map the constant energetic states of a uniform electric field. We return to the rule that moving a charge along an equipotential surface requires zero work. Physical work requires force applied over a distance, but only force applied in the direction of motion matters mathematically. To achieve zero work, no electric force can push along the surface. The force must be purely perpendicular. We apply this proof back to the point charge model to observe how this constraint dictates geometry. The schematic explicitly shows this 90-degree intersection at the surface boundary. This constraint permanently locks the vector field and the scalar surfaces in a perpendicular arrangement at every point in space. This logic leads to the final axiom: equipotential surfaces can never cross each other. Imagine two surfaces, one holding 10 volts and one holding 5 volts, intersecting in space. We isolate the boundary line where these two shapes overlap. This creates a contradiction. A single point along that line would possess two different energetic values. Because a point in space cannot possess two distinct scalar values, these geometric boundaries act as an uncrossable map. We see the spherical geometry of the point charge and the planar geometry of the uniform field as completed systems. While different charge distributions dictate different geometric shapes, the absolute rules never falter. In both models, the fields pierce the surfaces at a mathematically perfect perpendicular angle. Equipotential surfaces represent rigidly constrained geographic maps of energetic plateaus. Visualizing these boundaries allow physicists to instantly read the magnitude and direction of the underlying electric forces in any environment. The behavior of electromagnetism is built upon simple geometric laws, governed entirely by the demand for zero energetic work.